Welcome to Large Voxel Landscapes on Mobile, where we're going to talk about the terrain system that we use at Roblox, how we made it scale to larger worlds, smaller devices, and implementation decisions we've made along the way. Quick aside, what is Roblox? It's an online multiplayer game creation platform. Platform is keyword here. It means that the content is created by our community, not by us. We have a lot of users and we run on a lot of different platforms and use a lot of different graphics APIs. Now, for the purpose of this talk, we're going to mostly ignore the distinction between the graphics APIs because the terrain system is largely agnostic. However, it does have to cater to different devices in terms of them having varying amounts of memory or computational power. Here's a few screenshots from the content that our community has created. This is a screenshot from the editor with the game being edited inside it. And this is an imported height map from Mars. All of these use the same voxel-based terrain. The Mars screenshot is not to scale. When we started working on the terrain system a few years ago, we set a few goals, and the first very important one was no baking. So any portion of terrain can be modified at any point in time, might be through a script, might be through a physics-based impact, for example, explosion creates craters in terrains. We wanted a single system that fully supported 3D landscapes, so caves, overhangs, and all of this without mesh inserts. We wanted reasonably large worlds, but also we wanted these worlds to run on really small devices. So our low end at the time and today is an iPad 2, OpenGL 2 class device, weak GPU, weak dual-core CPU, and around 200 megabytes of memory total available for the game. Of course, we wanted the editor to have easy-to-use tools, but also very important for us was an existence of an API to manipulate terrain from scripts that was also easy to understand and use. For example, we want to support custom procedural generators, custom tools, destruction scripts, etc. And then for us, materials are more than just textures. They have semantical meaning, and so the more we could leverage that to make it easier to create terrain that looked visually interesting by using the material information, the better it was. So dynamism pretty much cuts out meshes, and then height maps are eliminated because we need fully 3D worlds, so voxels were mostly a no-brainer. What is in a voxel, though? So for us, every voxel has a material, which is an index into the palette, and occupancy, which is a 0 to 1 value. 0 means there's almost no matter inside the voxel, and 1 means there is a lot of matter inside the voxel. This is very small, compact, and easy to understand. Everything else that we do with terrain is just a function of those two, and of course the neighbors and various material-based parameters and whatnot, which makes it easier to create content, and also it makes it so that we need to store less data at runtime. Now, why occupancy? So when we started working on terrain, we evaluated a lot of different approaches, and we settled on this one. So we looked at material-only approach where maybe there's no occupancy inside each voxel, but here there's a limitation in that our voxels are pretty large. They are around 1 meter per side, and it's really hard to build good tools that give the content creator decent accuracy when working with terrain if you only have one material index per voxel. Sign distance is an obvious choice. Our occupancy representation is close to that, but it's simpler in that you don't have to worry about the voxels that are outside of terrain or deeply inside the terrain, so it's a bit easier to script. And then the other big possibility was to use Hermite data. So there's a paper, dual contouring of Hermite data, that describes an approach where inside each voxel you store intersections, or rather inside each edge you store intersections with the geometry, you store the position, you store the normal, and then you use that to reconstruct the original surface. This is great because it's very powerful and expressive, but it's really hard to reason about. It's hard to script. How do you write a procedural generator for this, etc.? How do you write good tools? All of these things weren't very clear to us, so we opted for a simpler approach that loses some of the expressive power. Here are some screenshots from early prototypes. So this is the Herman data prototype that we really liked because of the amount of control that it gave you, but it was hard to author content for this. And then this is a simpler implementation that we started with, where you don't have Herman data, you just have occupancy inside each voxel. And then you do an isosurface extraction. Now, before getting into that, how do we store the voxel? So we have a sparse and multi-resolution storage. Sparse means that we don't know what the world bounds are, we don't know where the content that's interesting is in, we don't even know if it's mostly a flat world or if there's a lot of depth to it. So we store it as a sparse set of fixed size chunks. Fixed size chunks are convenient for us as a unit of work, and then sparsity is important to support varying use cases. For each chunk, it's not just the voxel content that it stores for the base voxel resolution, which is like 1 meter, but it's also a full MIP pyramid in 3D. Because it's a 3D MIP pyramid, it doesn't add that much of an extra memory cost, but it's really important to have this. So one reason to have this is level of detail, which we'll cover. The other reason to have this is that it's infeasible to store the entire voxel landscape. Like the Mars level, I think, is 500 million voxels, and it's just too much memory to store on an iPad 2. So because of this, we have a streaming system that can unload and page in and page out individual levels in each chunk based on the proximity to the player and based on the available memory on the device. So it can say that the chunk that's close to the player needs all MIP levels, but the chunk that's really far away maybe only needs the very last one, or maybe one or two last MIP levels. So this is great at reducing memory consumption, obviously, but the image generation algorithms have to take some of this into account. Now, within each MIP, so you may think of a MIP as just a 3D array of voxels, and each voxel is just 2 values, so it's just 2 bytes of data. It's a bit more complex than that, because that tends up being wasteful. We have the streaming system, but then it's inefficient for the streaming system to unstream too much data. It's better that the data is more compact to begin with. So it's very common for us to see chunks where a lot of rows are not particularly interesting by themselves. They're filled with either air, so they're empty, or they're filled with some solid material, and it's the same material per row. Because of this, we use this row-based compression in memory, where if the voxel content inside a row of 32 voxels or smaller number in larger MIPS is the same, then we just store 1 byte saying this is the material in this row. Otherwise, we store a full 2 bytes per voxel. And of course, all of this has to handle modifications, arbitrary modifications from scripts or physics changes. So we have to either unpack aggressively or repack opportunistically when we need to. So now that we have the voxel data, how do we render this? Well, we can't really trace or like ray march this directly on the GPU. We could, but definitely not on OpenGL2 or an iPad 2. So we have to generate meshes, and we started looking into marching cubes, but didn't like a few aspects of the algorithm. The topology there is a bit too random, and we wanted a bit more control over the vertex placement. So instead, we ended up going with the dual method. This is inspired by the dual contouring of Fermat data paper and Naive Surface Net's blog post. This can, in theory, run on GPU and compute shaders, but in practice, again, OpenGL2 and OpenGL3 no compute, so we have to run all this code on the CPU. Here's in broad strokes how the algorithm works. I mentioned that there are 4 grass voxels and everything around this is air. Then we mark every grass voxel as solid with a black dot and every air voxel as empty with a white dot. Then we connect dots of different colors, or rather we connect dots together, and then for every cell that has some of the colors different between the corners, this is a 2D picture. Of course, the actual implementation is using 3D, and so there's 8 corners of a cell. But here, if it's not all black or all white, then the cell is active. Then we have to do 2 things. One is we have to place the vertex inside a cell somewhere. In this picture, we place the vertex in the middle of the cell, which happens to align with the corners of source voxels. And also we have to connect neighboring active cells together. In the 2D case, we have to connect them with lines. And then in 3D case, in our actual case, we have to connect them with quads, which is nice because this actually means that the topology of our terrain mesh output is just a lot of quads, tends to be a bit more uniform, nicer to work with in some cases. There are some extra optimizations that you can do for raycasts and such when you know that it's just quads. Now, so we place the vertex inside every cell. What kind of parameters do we set for this vertex? First, we need to pick the position, the normal, and also we said that we wanted just one material to correspond to every vertex. It's a simplification. In the earlier example, of course, that is just grass material, so it holds. But in practice, in real landscapes, there's many cases where there's conflicting material information that comes into generating the vertex, and then we just pick the dominant one. So then for the position, we start with what naive surface nets does, which is that if you look at the edges that connect black dots and white dots, you can place a point on this edge using the typical isosurface-based interpolation. For us, it's occupancy, and classically it's based on signed distances, but it's similar where you place the point. In this case, you would place a point in the middle of the edge if the occupancy was 1, to push it furthest out along the voxel direction, and then if it's 0, then you would place it really close to the corner of the voxel, to the center of the voxel. And then you can look at every cell, and every cell has a few edges that have these mismatching colors, and then you can take all of the edge points and then averaging of them together. So this is what naive surface net does, and this is what we started with. And then to compute the normals, we just average triangle. So this is very easy, very simple, gives you similar results to isosurface extraction from signed distance fields. Now, there is a lot of leeway in where you place the vertex though, and we aren't using that. So on this screenshot, for example, you can see that at the top, the terrain looks very blocked, and this is because this was what happens when you place the vertex in the midpoint in the center of every cell. And at the bottom, this is the averaged approach that we use from naive surface nets. Now, you can actually do a lot of things though with the vertex position. So in this screenshot, we are actually interpolating this decision or like the vertex position between these two choices based on whether the vertex is above ground or below ground. But of course, average and just placing the point in the center of the cell is only 2 options. So here's one more. Here's what happens when you take a random offset to the random based on the cell identity, and then apply it to the position and then constrain the resulting position to the cell boundaries, which is not necessarily crucial, but it helps to avoid self-intersections. And this also gives you a nice kind of different look to the terrain, nice different shape. And so inspired by these possibilities, we ended up doing exactly this, where we pick a material for a vertex, and then based on this material, we define a procedural deformation function that places the vertex somewhere within the cell. Maybe it's the center, maybe it's the average, maybe it's one of these shifted by a random offset, maybe we quantize it to some multiple, etc. There's a lot of different possibilities here. Here's just a few of those. This is great because this is where we start saying, it's not just the occupancy that matters, really the material choice defines the shape of the terrain, and so it makes it easier to build interesting looking terrain without too much effort. Also, we use the material information to define normal blending, so you can compute normals just based on the averages of the triangle normals, but then you usually have to have some sort of crease angle cutoff. In this case, though, we can say this material always has soft edges, or this material always has hard edges, and therefore needs to separate the triangle normals when averaging. This is an example of this in action. There's a few different materials here. There are some that use just smooth average position. The bricks use the midpoint, and then rocks use random offset. The pavement uses quantized offsets, so it has a bit more kind of man-made looking structure, but still not all that uniform. And then it's hard to see here, but the other material uses barrel, which is smooth on x and y, x and z, and then it's always the center along the y-axis, which means that when you build plateaus, the top is always pretty flat, which is nice. So there's a lot of different possibilities here that you can imagine. Now, okay, we have the vertex position now, and for every vertex we have the material index, but what do we do with this then? So here's the triangle, it has 3 vertices, each vertex has material. How do you compute the color? Well, so you have to sample textures from 3 materials and then interpolate based on barycentric somehow. But then what kind of projection do you use? What kind of texture mapping do you use? Because all of this has to be dynamic based on where kind of the points are. Well, the classical way to do terrain texturing that avoids distortion is triplanar mapping, where you have 3 projection planes, x, y, yz, and xz, and then you blend between all 3 of those using the normal. So then you have 3 samples from different materials, and then for each one you do 3 triplanar samples. And then, of course, this is not just albedo texture, there's also normal and roughness, and so you have 27 fetches. And even if you don't have albedo, even if you don't have normal and roughness, you still have 9 fetches, which is a lot for an iPad 2. So we do not do that. Instead, what we do is we use an approach inspired by quilting by the paper Real-Time Image Quilting from SIGGRAPH 2011. The basic idea there is that you take each vertex and then you look at the incident triangles and then you project a patch of textures onto that, and then in the vertex, in the center vertex, the influence of this patch is maximum, is 1, and then towards the edges the influence goes to 0. And then you overlay many different patches like this, and in combination of these end up defining your visions. So for each vertex we're gonna do only one texture sample. This means that for a triangle, we do 3 in total if you only care about albedo, and if we do 9 if we also care about normal and rough. Now, how do we make this projection? Well, we need to pick a projection plane, or the most obvious way to do this is to pick a projection plane. And we pick one per vertex to minimize the distortion. This doesn't result in triplanar mapping, but it can result in something reasonably close to triplanar mapping if you're careful in your plane selection. We could store a full plane equation, but instead what we do is we store a plane index and we just have 18 fixed planes. 18 is just the smallest number that worked reasonably well. Here's how this sort of looks like. Here's a single patch where there's a vertex in the center, and then there's a single projection plane, and then all triangles around this vertex end up sampling this texture with this texture projection, and then the blend weight depends on barycentric coordinates. And then if you look at the entire terrain with that patch taken out, you can see that there's a lot of space here that's just covered by these different patches, and you can imagine that if you added the previous slide to this slide, you would basically get the full resulting terrain. Now, one other thing that we'd really like to do, though, is to fix the tiling artifacts that happen far in the distance. And if you think about this, well, we already take a vertex and then we do some texture splat using a projection plane that we pick per vertex. Well, we also can augment this transform with a random shift and random rotate, and the randomness could be based on the vertex seed so that it's all stable. This helps a lot in breaking up the variation. And also this randomness could be dependent on the material. For example, if you have a brick, you really don't want to rotate the samples of the brick, but you can shift them just fine, especially if you shift by sort of brick-sized granularities in UV space. Now, if you imagine a triangle where the 3 materials in the corners are the same, effectively you end up having 3 different randomly rotated and translated layers all blended into each other, which breaks up the tiling very nicely. Here's how it looks. So here's the scene without the tiling, without detiling, where you can see a lot of tiling artifacts on grass, which you could try to hide with texture art, but it's really hard to do a good job there. And even on water, where we have several different layers of normal maps blended together, you can start seeing tiling artifacts if you look sort of close. And this is at this angle. At less at more oblique angles, you see tiling on even on water if you don't do anything to fix it. This is what happens when you apply the detiling. You can see on the water there's basically nothing that you can notice, no tiling issues whatsoever. On grass you can sort of see the lines somewhere where the texture rotations happen to align in such a way that some prominent feature of the texture is still visible, but it's largely speaking really, really good. And this is all completely automatic. Now, what we end up with is that for each pixel of each triangle, we do 3 texture samples, or we do 9 texture samples if you need full PBR texture set, but 3 material samples. And depending on the configuration of the triangle, they end up serving different roles. So if the materials are different, then we need to do this because we need to blend between the materials. If the materials are the same, we still need to do this because we need to do triplanar. And if the triangle is flat along the ground, so that you don't even need triplanar, these samples are still, and they do still end up being useful to break up tiling. If we are really desperate, which we are on some of the low-end devices with very weak GPUs, we can go one step further and say, well, we have 3 texture samples that we need to do, but really let's just do one with the highest weight. Of course, this is not great from the quality perspective. You see very hard seams between materials, etc. But if it's more important, if performance is more important than quality on some of these devices, then it's still a viable path that you can take, and we do take. Now, in terms of scaling up, so The biggest problem with this technique tends to be that the linear blend isn't great for a couple of reasons. If you have two different materials, blending between them just fades one texture into another, which is just not great because this is not really how the real world looks, how the real world works, doesn't look natural. If the materials are all the same, then the big issue is the contrast gets lost, and there's sort of, again, odd blends between different parts of the same texture you sometimes can see. We've experimented with two different approaches to fix this. One is height-based blending, where you have a height map that you can store in the roughness texture if there's an extra channel there, which there usually is. And based on the height of different materials, there is some region where you still do the blend, and there was some region where the blend is maybe more aggressive and one of the material wins early on. One alternative implementation is histogram preserver blending, which is the work by Eric Heitz. So the height-based blending mostly fixes blends between materials, but it also can help fix the contrast problems as well. Histogram preserver blending is mostly good for fixing contrast loss. Here's an example of how this looks like in action. So this is the vanilla blend, nothing special here. And then this is the height-based blend. And so if I go back and forth, there's two things that you can see. One is the transition between two materials is much more natural. The grass still sort of, it grows through the bricks, but in a more organic fashion, even though there's still some region where there's a blend. And the other one that you see is that the second screenshot has higher contrast, and this actually matches the real art, like the texture that we started from, better. So we've talked about the textures. Now, one downside with this amazingly beautiful scheme about, 3 textures, texture samples per triangle set, etc., is that hardware doesn't really want to work this way. So the fragment shaders usually don't expose barycentrics directly, they don't expose the vertex shader outputs. And to make all of this work, we actually have to pack a decent amount of information into each vertex. We have to pack effectively some information about the vertices in the same triangle, other vertices in the same triangle, into the vertex, and then duplicate that. This is not great for memory. This is not great for performance. We kind of have to do this. We experimented with alternative implementations here, so for example, using geometry shaders on desktop hardware. It worked pretty well. Substantial memory savings, comparable performance, maybe slightly better. But of course, geometry shaders aren't available on many mobile platforms, and then aren't advised on others. Hopefully, at some point in the future, it's either going to be that we can use mesh shaders if they ever happen on mobile, or one alternative implementation is to use direct access to barycentrics, which you do get on consoles. So in theory, some GPUs may be able to provide this. But short of either of that, there are some kind of hacks that you have to do, and we compensate for this by aggressively bitpacking data. Bytepacking. So then, Drockel-wise, again, OpenGL 2, iPad 2, weak CPU, pretty thick driver layer. We have to minimize that. To minimize that, we have to make the decision where every chunk is drawn in a single Drockel, and to do that, we have to pack all of the material layers used in the level into either an atlas or a texture array. We prefer texture arrays, of course, but OpenGL 2, OpenGL 3, OpenGL 2 mostly, so we have to use an atlas, and inside an atlas there, we have to leave large borders to have MIPS operate in terms of filtering. But when we can, we do use texture arrays. So this is great, both because it doesn't really matter as much what materials you use in your level, it roughly performs the same way, and also because all of the material information is kind of front-loaded and set aside in these atlases and texture arrays and constant buffers. So really for every chunk, you just have to update the uniform that corresponds to where this chunk is in space to make bitpacking possible, and that's it. So even if you do have to render many chunks, like hundreds of chunks per frame, even on OpenGL 2 class devices, it's still pretty fast on the CPU. Now, at some point though, you have to start introducing level of detail for a variety of reasons. So CPU cost becomes prohibitively expensive if you have too many draw calls. Of course, the GPU cost in terms of triangle count, and also because of the streaming system, we don't even have all of the voxel data always resident in memory, so sometimes we have to use voxel data that's not the top MIP. To organize all of this, we use an octree, and then we only render leaves of the octree, and then these leaves can be split when the leaf is close up, and then they can be merged if they're far away, which gives you these level of detail transitions. For us, every leaf that we do draw, we always match it as if it's 16 cube voxels, which is just a trade-off between the draw call size and the update cost. Whenever voxel changes in a chunk, we do have to update the entire chunk. Our meshing is not incremental, so there's a trade-off there, with 16 to 32 cubes probably being reasonable trade-offs. And the nice thing is that we do use the voxel data for this, so we don't have to go through the top highest resolution voxel data, create a high resolution mesh, then simplify that, etc. We can just take the downsampled representation of voxels that we already have in memory from the MIP pyramid and work with that. Now, the biggest problem, of course, is what do you do with the gaps between levels of detail? If the level of detail in the neighboring octree nodes is the same, then it's all very simple. Our meshing algorithm handles all of this beautifully. It has edge consistency, edge rules, and all of this. Now, if they're different, then of course there's going to be a gap between these two. Now, ideally, and this is what the dual contouring paper does do, you would generate triangles to stitch this gap precisely, matching vertices to vertices, etc. We do not do this. We do not do this for two reasons. One is it's really complicated to write this code, to get this code to be correct, and to get this code to be efficient. It's just very hard because it's a very complex topological problem, and there's cases you have to enumerate, and there's lots of branches that you have to take, and all of that. So it doesn't end up being very efficient, and it doesn't end up being very simple. But also this complicates the management of the LOD data substantially, because whenever an LOD switch happens, you now have to remesh the stitch between this chunk and some neighboring chunks. And you have to do all of this in time, because when you do transition from one level of detail to the other, it would be nice to do the transition simultaneously for everything that is a result of this operation, and all of this gets very painful to implement. So instead of doing that, we use the next best thing, which is skirts. So this is a classical technique from the height map rendering world, where you generate extra overhang geometry for individual cells, and then hope that that will cover the gaps. So for us, that just means one extra triangle, and we do this based on just one extra layer of voxels. We do some voodoo magic to kind of patch up the voxels so that the geometry ends up being more reasonable. But fundamentally, the geometry in skirts is not very reasonable for us, but it doesn't matter as much because we use depth bias to kind of hide it. We push it inside the screen so that if there's any non-skirt pixel, we draw that instead. This means that you only see the skirt geometry inside the gaps, and these gaps tend to be reasonably narrow to begin with, so it doesn't end up being a big problem. Also, this is using the exact same meshing code with all of the performance optimizations, etc. So it's actually reasonably fast, and it's cheap enough to generate for every chunk. It does come at maybe 10% extra memory cost, but the level of detail by itself more than makes up for it. Now, here's how this looks like in practice. And this is where the simplicity of this approach really comes in. So you see the LOD0 chunks and LOD1 chunks, and you see the the blue stitches between the 0 and 1. This is the skirt geometry. For every chunk, you need up to 3 of them, because for every chunk, we generate stitches from the finer level of detail, LOD0, to the coarser level of detail, LOD1. This means that for every chunk, there's 3 sides that point where the neighbors are within the same octree cell, and by the octree construction, these cells must be the same level or finer, so you don't need stitches there. So there's at most 3 sides that you need stitches on. And in a 2D picture, so there's the base, which is like the center of the chunk, and then there's stitch X and stitch C, and you only have to render them if either of your neighbors on either side needs stitching. So has a different level of detail, or rather a coarser level of detail than you are. Now, the beauty of this is that, okay, so there's at most 3 sides, and one of them, the Y side, the up, Y being up, is almost never used for us just because of how the level of detail is computed, etc. And if you order your index buffers for the stitch geometry and the base geometry in one consecutive kind of index range, stitch X, base, and stitch Z, then you can, if you only need X or Z or both or neither, it's still one single draw call to just adjust the index range. And so it's almost always still the case that we only need one draw call per chunk. We only need 2 if for some reason we need to draw the Y stitch. Of course, for this to work, you have to do this depth bias conditionally within the same dockle, but this is actually fine because for us, it's just that the vertex shader pushes this geometry into the screen and can do this based on one bit that is stored somewhere inside the vertex that says, is this a stitch vertex or not? So this covers most of the basic terrain, etc. Let's talk about a couple of examples of where we take the material information that we have and do something material specific, very material specific with that. So one example is water. Water in general doesn't fit very well with this framework of meshing. By if you just say, well, we mesh the interfaces between solid and air, well, water is not solid. So to make water work, we really have to mesh the interfaces between solid air, solid water, and water air. Solid water is important for underwater rendering, and then water air is important for actually drawing the outer surface of the water. And all of this can actually be done during the same single meshing pass, which is really nice because it doesn't actually cost more performance, much more performance, I should say, to extract water geometry as well as solid. Instead of 2-color solid air, we just use 3-color solid water air. And whenever there is a difference between the colors on the interface between two voxels, this is where we know that we need to place quads. Now, we do need to render the water separately. I mean, it's translucent, it has separate shading, etc., etc., etc. So this is where we actually do use 2 draw calls per chunk if a chunk has water and non-water materials. And there's some care that has to be taken due to some specifics of how we mesh all of this. So if you were to apply this naively, something you would see is water bulging. Not sure if this is very obvious here, but there's a ground that goes kind of down, and then there's a connection with water, and then the water grows back up. And this is just because of how the averaging in the naive surface nets work with the positions of the edge points. But you can fix this by doing a water-specific deformer because we know the material and push the water down and it ends up looking nicer and more like a lake. We play some other small tricks here with geometry generation, although there's still some space to improve this because these connections sometimes end up looking a bit finicky. For water rendering, there's nothing very unusual here, I would say. This is where we do start seeing some desktop-only features. So in general, we use tiled animated normal maps that we have pre-baked once, just based on a wave simulation. We have a lot of vertices in general in terrain. It's reasonably uniformly spaced vertices, so we might as well use them by displacing them to do geometric waves, and then there's some extra underwater and refraction simulation. So on desktop, where we do have the depth, we can also do screen space refraction and screen space reflection with an 8-tap trace. One big aspect, 2 big aspects maybe in water rendering that we will improve on in the future is flow in general and shorelines in particular, where we actually do have some information about which vertices are on the border and which aren't. And in this case, you can see a bit of a darkening that we apply in the border. So we can place foam automatically and things like that. We haven't done that yet. This is how the underwater shot looks like. This is why it's really important to mesh the solid water interface, otherwise you just won't see this. And this is, here you can see the underwater fog and sort of reflection, refraction accidentally sort of working in the underwater simulation. And of course, this being voxels, there's no real restrictions of what you do with water and where you can place them. So this is an example of just there's a water bubble that doesn't fall down because we don't have fluid simulation quite yet, but you can see refraction and other effects here as well. So past water, there's also a question of general geometric fidelity and kind of terrain looking interesting beyond the textures. And there's a lot here that we can do in theory just based on the materials and tessellating things more and creating formations that are visually interesting based on the material. But one very obvious thing to do, which is what we did do already, is to do clutter or foliage, or in general, we want a lot of small objects automatically placed on terrain based on the voxel types of the material. We experimented with card-based grass, and it can look really nice if you have a decent texture and you have to be careful of how to organize the mesh, etc. But then when you run any card-based grass, despite it doesn't matter if you use blends, it does matter, but it doesn't matter as much if you use blends or discards, it still ends up being substantially slower than geometric grass on tilers, specifically on deferred tiling architectures where the hidden surface rejection pass can remove a lot of the geometry that's not visible. If you do card-based grass, you mostly just don't use that, and so that's not great for performance. So we like the look of card-based grass a bit more, but we ended up going with geometric grass just because it's much more performance friendly and we can actually ship this on mob. Here's how grass looks like. So this is a dense field where you can see some animation and some shading experiments. And here's a much less dense field with a bit of a different kind of structure and running with the rest of the environment as well. So grass ends up being a bit of science and then a whole lot of kind of art and a whole lot of work to make it look just right without paying too high of a performance cost for it. We do end up rendering individual blades, but of course we compact all of these blades into larger index buffers, vertex buffers and index buffers. And then each blade is just 3 to 5 vertices per grass blade. 3 is like the simplest one, and 5 is the simplest grass blade that you can still bend, which is really nice up close. Important point is that when we place the grass, so we place it based on the triangle surface that's generated by the mesher, but you have to be really careful and use stable randomness. So we see the random number generated using the seeds that come with the vertices. The reason being, if you imagine a chunk, and so whenever anything changes inside the chunk, you have to regenerate the entire chunk. And then if there's a crater in a chunk that wasn't there before, you really don't want that to affect other parts of the chunk where grass used to grow and it should still grow, and it should grow in the same places. And then shading is just a whole lot of tricks, a whole lot of tuning. There's wrap diffuse that we do. We do translucency simulation sort of, but it's an approximation that's pretty cheap with a few LU instructions. And then a lot of the interesting visual variety in grass tends to happen because of the clumping of grass, and you have occlusion. And of course, all of this is very, very hard to actually simulate on a mobile device. So we do a lot of height-based approximations for this with gradients for diffuse and specular and normals that are slightly different from the geometric normals, etc., etc. I don't have a lot of time to go into more details, but here's a beautiful picture of our rendering engineer who worked on all of this, studying the light interaction with the grass blade. So we're pretty happy with where we are with terrain in general, but of course there's a lot of work still to be done. A lot of this was focusing on kind of what is practical on old mobile devices, on ES2 class devices, maybe ES3 with not a lot of power, but of course the technology has moved since then. And also there's a lot further that we can push this on higher end desktops, right? So high fidelity geometry is something we want to explore, where we can actually tessellate the geometry, the terrain geometry more in various ways. Shading is something where it's very easy to make a lot of kind of progress in various places. I already mentioned some improvements on water. Texture mapping is interesting because in general, we're very happy with the texture mapping scheme that we kind of landed up on. But it does right now, due to how it's implemented, does mean that in some cases you do see stretching on some triangles, and it could have been mapped a bit better. And of course, one big general theme in Roblox is that as we develop the platform further, our users and we want larger and larger ones. And so right now, the practical limitations of the system are perhaps around 1 billion voxels with the streaming system, paging things in and out, etc. Like, this is reasonably practical to achieve today. And so if you imagine a 10 square kilometer world, this is fine. But if you imagine a 100 square kilometer world, then for each 1 by 1 meter, you get like 10 voxels. And 10 voxels is not enough, because that's just 10 meters of depth information, and you really want 100 or more. And so figuring out better compression schemes and in general smarter ways to do level of detail where maybe we lose less fidelity of geometry for similar performance and memory gains would be interesting to explore. So that's all I have. Thank you for listening to the presentation.